For the final project, we have studied on predicting helpfulness of Amazon product reviews. In this video, I would like to share our findings with you. Basically, I will start with our motivation and give you a big picture of questions we have studied. Then I will briefly go through how we pre-processed our data and what methodologies we have used. After that, I will present several empirical results of our experiments and conclude with the best model for predicting helpfulness of product reviews. Finally, I would like to propose several improvements that can be done in the future. Many websites such as Amazon ask users to rate and comment on the products. Despite of the high volume of comments, the quality of comments are not guaranteed. Therefore, websites like Amazon allow users to vote on the helpfulness of reviews so as to provide new customers with information of higher quality. However, one crucial problem is that many new or less popular products do not have sufficient votes on review quality. We believe displaying the reviews with higher quality will not only enable users to make a better purchase decision, but also provide producers with better feedback on how to improve their products. Our project is guided by two important questions. First, what features will have a great predictive power of whether a review is helpful or not? For example, how do we identify rational comments from emotional comments? Second, which classification algorithm will perform best in terms of the accuracy of helpfulness prediction? Before we talk about methodologies, let's first take a look on the dataset we use. Here we use the Amazon product dataset provided by Yueying from UCSD, and we will focus on one product category, app for Android, and we randomly selected samples with at least 20 votes for helpfulness. Here is a sample entry of reviews. In this project, we will focus on 3 columns: helpful, review text, and overall review score. Column helpful defines the ratio of positive votes, or the helpfulness score. For instance, the interval 29 and 35 means 29 of 35 persons vote on helpful, while the other 6 persons vote on unhelpful. For those with a helpfulness score greater than 0.75, we will classify as helpful, and for those smaller than 0.75 as unhelpful. Whether a review is helpful or not is what we want to predict. Column review text is used to derive feature words. Column overall is customers' rating towards the products they purchase. The rating ranges from 1 to 5. It is used to derive sentiment features. Now let me introduce methods used in our model training. Before training weights, we first need to extract features from text as inputs of the model. It is often the case that the length of reviews is in proportion to customers' efforts devoted, and thus determines the quality of reviews. Therefore, we first consider text structure features. Here we counted number of characters, number of words, and number of sentences. In addition to gauge the net understandability, we also counted automated readability index as a text structure feature. Furthermore, in reality, we find that comments containing much personal emotions are often irrational and may be unhelpful. Therefore, we extracted sentiment features from the text, including whether there is an exclamation, question marks, or capitalized words, and customers' rating to products as sentiment feature. Now we have all the features and we can move on to weight training. Here we tried 4 classification algorithms: logistic regression, naive Bayes, support vector machine, k-nearest neighbor. The first 3 methods are supervised learning, while k-nearest neighbor is the unsupervised one. To come up with the best predicting model, we did some experiments with different classification algorithms, input size, and features. First, we compared performance of 4 algorithms. As shown in the graph, regardless of training data size, logistic regression has the best performance out of 4. When data size is around 8,000, validation error reaches its lowest level for 3 out of 4 algorithms. Moreover, when data size keeps increasing, the model seems to perform worse. During experiment, we found that there are much more reviews labeled as helpful than unhelpful. The unbalanced data will probably impede our progress in predicting unhelpfulness. Therefore, we use the method of oversample to adjust the distribution of dataset, and we compared originally sampled data and oversampled data. As a result, we found that the rate accuracy improved for unhelpful reviews, but slightly decreased for helpful reviews. Overall, the validation error is lower with originally sampled data. There seems to be a trade-off between better prediction on less helpfulness and better prediction on helpfulness. Then we tried whether keywords in comments can help us improve our prediction. Basically, we want to know whether people's comments content will be helpful in our prediction helpfulness. Here, we removed all punctuations, eliminated stop words, tokenized strings, decapitalized and lemmatized words to avoid duplicate meanings. According to other literatures on natural language processing, many of them use the method of TF-IDF. The TF-IDF value increases proportionally to the number of times a word appears in a document and is offset by the frequency of the word in the corpus, which helps to adjust for the fact that some words appear more frequently in general. Again, we train on 8,000 originally sampled data. Consequently, we find that for all 4 classification algorithms, the model performs better without the content feature. In other words, the bag of words does not improve our prediction accuracy. To summarize, our best predicting model is the logistic regression using 8,000 originally sampled data with features including text structure and sentiment features. During this project, we spent most of the time to do experiment by changing features, data size, and algorithm. However, there are some other things we can do to improve the model performance. First is the choice of dataset. Recall that in this project, we used the data on apps for Android. However, there are more detailed categories among these apps, such as game, education app, shopping apps, and so on. Keywords to express these apps vary a lot. Therefore, it would be helpful if we can study on the more detailed categories separately. Second is the computational effort. Our computers are unable to run smoothly in terms of a huge dataset. More things could be done to decrease the computational effort. This is basically what we've done in our final project. Thank you for watching.